All right, welcome to calculus. So we're going to look at work. Namely, this is the more of a physics definition of work as opposed to other definitions that do exist out there. So really what we want to do is we want to pay attention to what are the processes in place when we deal with, say, integration. And the idea being with integration, and this is just a real quick reminder of what we're doing, is that when we integrate two values, or when we integrate two values, when we integrate a value, say from a to b of some function of f of x, what we're talking about this being is essentially the, how do I want to say this, an infinite sum of individual parts and pieces. If you remember, this was the limit as n goes to infinity of the summation from k equal 1 to infinity of, and I'm just going to call it stuff for lack of a better word right now. That's not mathematically accurate or precise or anything, but right now what I'm really wanting to focus on is the fact that when we do integration, what we're really talking about doing is doing an infinite number of summations of small, tiny increments of pieces. When we talk about doing work, it's more than just, like if you wanted to lift something up and put something down, that is, you've done work. How much work have you done? Well, it depends on a couple of different things. It depends on the mass of the object, and it also is determined by how much movement the object has been pushed through. So for for an individual to lift up a 50-pound weight to 4 feet off the ground versus that same 50-pound weight 6 feet off the ground, they've done more work to lift it to 6 feet. So if you're talking about doing, say, a deadlift, and you lift the 135 pounds up to full height on that deadlift, just simply means essentially you bend down, you pick up the bar, and you pull back on the bar, lifting it up as you go. That is going to be dependent upon your height. The shorter person is literally, physically going to do less work to lift up the same amount of weight as the tall person. The tall person is going to do more work than the shorter person because they have the bar is going to have a longer distance to travel to get up to height for full extension. So that's the idea behind work. So we need to make sure we had a decent understanding of that process. Now, when we talk about doing work, a lot of times we're almost always or exclusively talking about the force that is involved in the process. So let's just work through an example here on work, pardon the pun. All right, so let's just say that there's a particular process and it requires 40 newtons of work. Okay, and this particular process, let's just say this is related to stretching or compressing a spring. Okay, and this is the 40 newtons of force is a spring, and this takes it from its natural length of 10 centimeters to its stretched length of 15 centimeters. So the idea being here is that you have a spring attached to something, an immovable object, a ceiling or something like that, and you have this weight, and this weight has a downward force of 40 newtons. Okay, that's what this is talking about. And when we put those 40 newtons on there, the spring stretches from its standard 10 centimeters to 15 centimeters in length. Okay, and I have meters, it's supposed to be centimeters. Okay, so the idea being here is that this 40 centimeters or this 40 newtons causes that 5 centimeters of stretch. And the idea of this 5 centimeters of stretch is important to us. We'll come back to that in a second. Now, one of the things that we need here is Hooke's law. And if you're not familiar with Hooke's law, don't worry. It's not a huge thing. For any homework problems that you would have in my class, you can always go back and you can look up those formulas as you need it. In particular problems, that's what we do in the real world. When we need a formula, we just go look it up. So what we're dealing with here with Hooke's law is the idea that this stretch, of course, the stretch factor is connected to a function. Oops, that's not a function. We have some function f of x, which is k times x, meaning that this is a linear relationship. At least for right now, we're saying it's a linear relationship, okay? So when we say it's a linear relationship, we're referring to is that the farther we stretch this out, the more force it's going to take. That's all we're really saying about that aspect of it. And we already know a data point. We know that it has been stretched out 5 centimeters. Now the thing about this formula here is it's actually based upon meters and not centimeters. So we're actually going to go back and we're going to switch this stretch here from 10 centimeters to 15 centimeters to meters, which means it is a stretch of 0.05 meters. Okay, notice we're going from 10 to 15. So the idea here is that 10 is our 0 point, if you will. That if we compress our spring upward there, that would take force as well, and that would be negative lengthening, if you will. Okay, so that'd be negative values to shorten it. So if we were to go to 2 centimeters, that'd be negative 8 centimeters of the stretch that we would do here, if that makes sense like that. So this is 0.05 of a stretch, those are meters, our K value, which is unknown to us right now, but we do know that took 40 newtons of force. And these would be known values that we could probably find just simply by attaching the spring to something and stretching it out. And then we'd solve for K, and we'd find that K is equal to 800. Okay, now we have this formula right here for this particular spring. This spring is F of X is equal to 800x. And there is the stretch equation, if you will. This is using Hooke's law to determine the stretch equation for this particular string. Now we can determine the work that is being done over any interval now that we have this equation. So it's 800x dx. Remember, we want the dx on there because that's our adverb that's telling us what we're integrating, right? Now let's just say that on this instance, we want to find the work, okay, to stretch it from 15 centimeters to 18 centimeters. Okay, stretch it from 15. So we've already stretched it from 10 to 15, which took 40 newtons of work. How much work are we going to do in order to stretch it from 15 to 18? Okay, and keep in mind that this work piece, in physics and in chemistry, we're going to measure this in terms of joules. So our answer here, our unit here, when we're done, is going to be in terms of joules, because that's how much energy is being required of us to do this work. So here, we're going to integrate this from 0.05 to 0.08 and 800x dx. Now, a couple of you may, as I wrote that down, may have started to yell and scream, where did 0.08 come from? Remember, 10 is our zero out point, right? So this is, if you will, this value right here, where we are over here on the right is where I'm drawing this. Let's just say this point right here where the spring is 10 centimeters long, this is 0 amount of stretch, okay? 0 centimeters from neutral, okay? Here at 15 centimeters, we are 5 centimeters from neutral. At 18 centimeters, we would be 8 centimeters from neutral, okay? That's what we're measuring, is the distance from neutral. Okay, so we're going from 5 centimeters from neutral to 8 centimeters from neutral, which corresponds to the spring being 15 and 18 centimeters respectively in length. Okay, so that's where those values are coming from. That's why we're switching it like that. And keep in mind, we're measuring this in terms of meters, and these values over here are in terms of centimeters, so we have to do that conversion first, which is why the metric system is nice in these instances, because they're easy calculations to do there. So now what? Well, now we just do the integration. So this is going to be integration that'd be 800x squared over 2, evaluated from 0.05, 0.08. We just plug in at this point, right? So that means we do a little simplifying here. That gives us 400, and that'd be 0.08 squared minus let's do 400 times 0.05 squared, all right? And we could have written that a couple different ways, but that way works out just fine. And we end up with the work that we're doing there to be 1.5 joules. Okay, and that's how much work was done in that interval. Okay, so, and we could have also done the same calculations to figure out how much work was done, how many joules, how much energy was expended just in that first 5 centimeters as well. We could figure it up for the entire length. So we could answer a lot of questions just simply by changing these values here, right? So take this one right here and just move it over here. And let's say, well, if we want to integrate from 0.00 to 0.08, that is the work for 8 centimeters of stretch, right? If we wanted to go from, say, 0.00 to 0.19, well, what are we doing there in that instance? Well, that would have been doing the exact same process. We still would have been using the 800x dx, right? But what we would have been doing in that instance is we would have been going from 10 centimeters to 29 centimeters. That's how much we're stretching the spring. Okay, so there's a lot of things that we can do with this in terms of work, and it's a very straightforward process. This isn't always the exact equation you're going to use. Sometimes you're going to use a different equation, but that equation should be easily found at any given time. Sometimes that equation is just a given equation. It's just said the force is blah, blah, blah. Here's the equation. Use this. And all it means is do the work. You're doing the exact process that we just went through, and maybe in that instance it's the units you come out with instead of joules. Maybe it's foot-pounds of torque or some other value. And they're for the most part, they're pretty straightforward to work through. I hope this was helpful. I hope this was useful. If you need additional explanation or additional problems worked out on this topic, please feel free to reach out and ask for additional ones, and I'll do my best to get those posted as I can. Take care.